So welcome everybody to this latest video on 162 Maths, and in this video we will go through the AQA AS Maths exam of 2021, Paper 1 Section B, which is the mechanics section. Now before we get started, a little reminder that there will be a question breakdown of Section B in the description, so if you struggled or couldn't do any of the questions, you can see which topic it relates to. There will also be a link to the 162 Maths contents page, which gives you easy access to all the videos of the lessons of the AS Maths curriculum, along with A2, and links to all the other AS paper walkthroughs. Question 10. Two forces, we have 3 -2 newtons and -7 -5 newtons act on a particle. Find the resultant force. The resultant force is found by adding these two forces, so if we add 3 and -2 and -7 and -5, 3 add -7 is -4 and 2 add -5 is -7. So that gives us the second answer. Question 11. Jackie says a person's weight on Earth is directly proportional to their mass. Tom says a person's weight on Earth is different to their weight on the moon. Only one of the statements below is correct. Identify the correct statement. If we look at what Jackie says, she's saying that a person's weight is directly proportional to their mass. Now a person's weight is mass times gravity. Gravity is that constant of proportionality here, so that statement that Jackie makes is true. And a person's weight on Earth is different to their weight on the moon. So if we look at mass times gravity, gravity on Earth has a different value to gravity on the moon. Therefore, Tom has a correct statement, so they're both right. Question 12. A particle P lies at rest on a smooth horizontal table. A constant resultant force F newtons is then applied to P. As a result, P moves in a straight line with constant acceleration 86 meters per second squared. 12a. Show that the magnitude of the acceleration of P is 10 meters per second squared. For the magnitude of acceleration, we want to take the values of 8 and 6 and apply them into Pythagoras. 8 squared plus 6 squared square rooted. If we do that, we get the square root of 64 plus 36, which is the square root of 100, which is 10, which we needed to show. For part 12b, it says find the speed of P after 3 seconds. In terms of SUVAT, if we consider what we are looking for, we've got S, U, V, A, T, we've got acceleration, we've got 3 seconds, and we want to find the speed. We're told that particle P lies at rest, so we've got these initial values. So let's pop those in. So initially 0, A is 10, and T is 3 seconds. So using V equals U plus AT, V is equal to 0 plus 3 times 10, which is 30. 12c, given that F is equal to 1.5 newtons, find the mass of P. So if we consider F equals ma, we want to use 1.5 in that vector form is equal to mass times the acceleration when that was in its vector form of 86, and m has to have a value of 0.25 because 0.25 times by 8 gives you 2, 0.25 times 6 gives you 1.5. There is a second way which you may prefer, and that is to find the magnitude of the force, so using 2 squared plus 1.5 squared square rooted, that gives you a value of 2.5, and if we put that into F equals ma, 2.5 is equal to mass times by acceleration, which had a value of 10. Therefore, mass 0.25 is the same answer. That would have units of kilograms, 0.25 kilograms. Question 13. A car initially at rest is driven along a straight horizontal road. The graph below is a simple model of how the car's velocity, v meters per second, changes with respect to time t seconds. Question 13a. Find the displacement of the car when t equals 45. So we want to work out the displacement, and so we want to consider for the displacement the distance above the axes and the distance below the axes. So our displacement, we're wanting to look at the distance above the axes and we want to look at the distance below the axes, and then we can consider the difference between the two to be the overall displacement. We can consider the distance above the axes as a forwards motion, the distance below the axes as a backwards motion. Therefore, the overall displacement, the change of the position from start to finish, must be the difference between those two distances. So our first distance above the x-axis is the area of the trapezium shape. Now, you can use the area of a trapezium, or you could split this into triangles and that rectangle in the middle. But we have a trapezium, so that would be the two parallel sides. They have distance of 32 and 10. We halve that and multiply it by the height, which is 12. If you type that into your calculator, you get an answer of 252. So that is the distance travelled. If we then look at the distance below the axes, if we then consider the area of this triangle, that is an area of the triangle which is half times the base times its height. So using those values on the axes, we've got 13 and 8, and half times 13 times 8 is 52 metres. Therefore, the displacement that we want to find is the difference between 252 and 52. That would be 200 metres. 13b, Shonda says, this model is too simple. It is unrealistic to assume that the car will instantaneously change its acceleration. On the axes below, sketch a graph for the first 10 seconds of the journey, which would represent a model more realistic. So we know that the graph will finish at 12 metres per second at a time of 10 seconds. So we want to consider roughly on this graph where 12 metres per second is in line with that 10 seconds. So we want to get that in this location, and I would, with a ruler, draw those two dotted lines so that they would be a little bit more accurate than what I've produced here. So you want to start at a gradual increase and it will tailor off. Question 14. A particle P is moving along a straight line such that its acceleration a metres per second squared at any time t seconds may be modelled by a equals 3 plus 0.2t. When t equals 2, the velocity of P is k metres per second. Question 14a. Show that the initial velocity of P is given by the expression k minus 6.4 metres per second. We're going to use velocity is the integral of acceleration with respect to time, because we're looking at variable acceleration here. It has acceleration and it has t in its expression. So we're going to integrate 3 plus 0.2t with respect to t. That gives us v is equal to 3t plus 0.2t squared over 2 plus c, that constant of integration. Now we need to look at the information given in the question to determine what the value of c is. We're told that t is equal to 2 and the velocity is given as k. So we can replace t with 2 and we can replace velocity with k. K is equal to 3 lots of 2 plus 2 squared times 0.2 divided by 2 is 0.4 plus c. So k is equal to 6.4 plus c. So our constant of integration is k minus 6.4. Now if we put that back in, so v is equal to 3t, tidying up the 0.2 divided by 2 gets 0.1 t squared, and that constant c we have now as k minus 6.4. Talks about the initial velocity, show that the initial velocity, in other words meaning t is equal to 0. So initially, so when t is equal to 0, we want to find v. So replacing t with 0 will mean 3 lots of 0 is 0 and 0 squared times 0.1 is 0. So we have v is equal to k minus 6.4 as required. Question 14b. The initial velocity of p is 1/5 of the velocity when t equals 2. Find the value of k. If we take what we have then, so initially the velocity was k, that was told in the question. So if we want to find 1/5, we have 0.2 as an equivalent decimal, and the time t equals 2 produced a velocity of k minus 6.4. There's the equation. We now just need to solve for k. So this is the solving equation where k is found by, I take 6.4 and the 0.2k and combine it with 1k, so that's 0.8k, and therefore k is equal to 8. Question 15. A box B of mass 4 kilograms lies at rest on a fixed, rough, horizontal shelf. One end of the light string is connected to B. The string passes over a smooth peg attached to the end of the shelf. The other end of the string is connected to particle P of mass 1 kilogram, which hangs freely below the shelf as shown in the diagram below. We're told B is initially held at rest with the string taut. B is then released. B and P both move with constant acceleration a meters per second squared as B moves across the shelf, experiencing a total resistance force of 5 newtons. Question 15a. State one type of force that will be included in the total resistance force. As the shelf is being described as a rough shelf, so it mentions in the question that the shelf is rough, so it's got a rough surface. Part of that resistance force would then mean it involves friction. Question 15b. Show that A equals 1. For this we need to set up a system of simultaneous equations, and we need to use a diagram to add in where those forces will be acting. So let's add in these forces. So we have tension acting on the string, and that is going to act in the directions as described. We have our resistance force, which we've talked about being friction. It says in the question the total resistance force is 5 newtons, so that's going to act in the opposite direction of the movement. We know that acceleration is being described as A, and the box B is going to move towards the peg as the particle P is going to move downwards. So the acceleration downwards for P is also the same value A. The vertical force acting downwards from P is just 1 times G, or G, newtons. So we want to set up this simultaneous equations in order to show that A is equal to 1. So if we consider what is happening on the box and we look at B, so if we consider what's happening for B, we have those forwards and backwards forces. So T minus 5 is equal to mass times acceleration. So our forwards force minus our backwards force is equal to mass times acceleration. Then if we consider the particle P, we have force T and force G. And we need to consider that the force is now acting downwards, so it's our downwards force minus the upwards force is equal to mass, in this case is 1, times acceleration A. So within this system of simultaneous equations, what we want to do is we want to solve to show that A is equal to 1. Now we want to eliminate T, and the quickest way to eliminate T is to add these two together. So if we add together these two equations, we can also replace, because it tells us within the question, it tells us here G is equal to 10 meters per second squared. So where we've got G, we can replace that with 10. So let's do that. Now if we add these two equations together, we end up with negative 5 add 10, or 10 take away 5. T add a negative T will cancel out, and that's equal to 5 lots of A. Divide both sides by 5, A equals 1 as required. Question 15C. When B is moved forward exactly 20 centimetres, the string breaks. Find how much further B travels before coming to rest. For this, we need to split up the process into the different SUVAT parts. We have the SUVAT part, if we take the information given in this part of the question, we're told that it moves forward 20 centimetres. So in metres, that will be 0.2. We're told that initially everything was at rest. That was told to you in the question. So U is equal to 0. And we know that A is equal to 1, which we've just proved in the question before. What we want to know is how fast the box is travelling before the string breaking. So what was the speed at which the box was moving at? So we want to find V. So using S, U, V and A, we're going to use V squared equals U squared plus 2AS. So substituting those values in, V squared is equal to 0 squared plus 2 times 1 times 0.2. V squared therefore is 0.4. And we can work out V by taking the square root of 0.4. And if we want to then consider what's happening once the string has broken, so in our second part of this question, so we want to work out how far it's travelled before it comes to rest. So we've got u, which was the end speed of square root of 0.4. When it comes to rest, its final velocity will be 0. And we've got a and t. Now we can use a from f equals ma, because at the moment we haven't got a. So we want to find a from f equals ma. So if we consider what's happening from the box, if the string has broken, the only force acting on the box was that resistance force of 5 newtons, so it would have a value of -5, and that will be equal to its mass times acceleration. So -5 divided by 4 gives us an acceleration value of -1.25. So now we have a is -1.25. SUV and a, we're going to use v squared equals u squared plus 2as. V is 0, so we have 0 squared equal to u squared, which is 0.4, plus 2 times a times s, and s is what we want to find. And we can then have 0.4 minus 2.5 s. So s is 0.16 meters or 16 centimeters. Question 15D. State one assumption you have made when finding your solutions in part B or C. We can mention about the string in these assumptions. So we could make the assumption that the string is inextensible. It tells us that the string is taut but doesn't mention inextensible in the question, so we could use that as an assumption. Or the second assumption is that the string is at all times parallel to the table. Either one of those two assumptions will get you the mark.